Okay, I'm back. I have to laugh at myself. When I'm doing these videos, I'm actually at home, and that was the phone, and I'm very sorry, but I had to answer it. So I'm going to come back and pick up where I left off. We talked in segment 5 about this business of sharing and that it's not necessarily equal schmequal. Okay, so where I left you was ionic means no sharing at all. So if I go back to my visual aid with my low-tech rubber band, here my left finger is just going to say, I'm not going to share at all. I'm going to pull so hard on that sharing connection that I'm actually going to take that electron. So you see we're not sharing at all. My left finger is negative. It's an ion. My right finger is positive. It's a cation. So that's what we saw before. In this visual aid, my left finger is negative, my right finger is positive. Okay, that's this scenario. My other scenario is my right finger is going to pull and say, I'm going to be so unfair that I'm just going to take that electron from you. Now my right finger is negative, my left finger is positive. Okay, so my right is negative, my left is positive. Now we looked at this before with metals. Metals always lose electrons, so they are the positive. The non-metal will accept that electron and they're negative. But the question is, how do we know if we're going to have this scenario, this scenario, this scenario, this scenario, or this scenario? How do you know if there's going to be equal, unequal, unequal, or no sharing at all? How do you know? Well, it has to do with what we call electronegativity. And electronegativity is the ability to attract electrons. Okay, so the more electronegative, the higher the ability to attract electrons. So in this scenario, neither one has a better ability. In this scenario, this has a better ability. In this scenario, my right finger has a better ability. So we're going to ignore my dogs. I'm so sorry, but we're going to ignore them. And we're just going to keep going. All right, so you have an electronegativity chart. And what you want to notice about that is as you move across and up the chart, that when you get to this area of the periodic table, fluorine, you become more electronegative. And for the most part, we're going to ignore the metals, right? Because metals will form ions. Hydrogen, however, we don't want to ignore hydrogen because hydrogen is part of your covalent compounds. Okay, so what you're going to do is you're going to look at the difference. It's a relative strength. Is this one stronger? Is this one stronger? Or is there no difference at all? And our magic number in the difference is 0.4. 0.4 is the difference between the carbon-hydrogen bond. So carbon is 2.5. Hydrogen is 2.1. So the difference, 2.5 minus 2.1 or 2.1 minus 2.5, we're going to take the absolute value. Whether I pull this way or that way, the difference is 0.4. And we're going to call that non-polar. So if it's less than or equal to 0.4, we're going to call that non-polar. That's like saying if you're in an arm wrestling or tug of war that neither team is going to win. You are of equal strength. Okay? Now I'm going to put 1,000,000 stars by this to tell you that you need to remember this for all eternity. Carbon-hydrogen bond, nonpolar, 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 nonpolar. And repeat it to yourself 15,000 times. And I'm kind of kidding, but not really. Because recognizing that the carbon-hydrogen bond is nonpolar saves you a lot of drama moving forward. Now, carbon-carbon, it should be very intuitive that anything like nitrogen, nitrogen, hydrogen, hydrogen is going to be whatever that number is minus whatever that number is, and the electronegativity difference will be 0 in all scenarios, and all of these will also be nonpolar. Okay? Now, what happens though when you have other types of elements in your covalent bond, like nitrogen, hydrogen? So go back to the other page and look up nitrogen, and you're going to see that that's 3.0. Hydrogen is 2.1. So 3.0 minus 2.1, or 2.1 minus 3.0, we're going to take the absolute value. In either scenario, what that means is the difference is 0.9. That is above 0.4, which means this is polar. Okay, so from my visual aid, what that is saying is that the nitrogen has a better ability to pull electrons. Okay, so our nitrogen is going to be partially negative, where my hydrogen will be partially positive. Partial negative, partial positive. Okay, so if you deem something nonpolar, there is no separation of charge, and you do not put any separation of charge over here. Here, I put my hydrogen with something that was stronger. So it gets a partial positive, this gets a partial negative. Okay? Carbon is 2.5, oxygen 3.5, so the difference here is 1.0. Whether I have subtract it this way or this way, you always take the absolute value. This is polar. Oxygen is higher, partial negative, partial positive. Okay? Lithium, for illustration, is 1.0. Fluorine is 4.0. The difference is 3.0. This is ionic. Now, our rule of thumb is that if it's about 1.7-ish or higher, we're going to call that ionic. Okay, so it's a little bit vague, but if we go back to our little rubber band, it's a continuum. The more I stretch, the more ionic-like I become. So this is called ionic character, and we're going to ignore that for this class. Okay, so we're going to say at about 1.7-ish, this is so stretched that we're just going to call that ionic. Okay? And then let's come back to oxygen, hydrogen, 3.5, 2.1. Our difference is 1.4. Whether we subtract this way or take the absolute value, we're going to call that very polar. Okay, so it's kind of like a passing grade. A passing grade can be really good, like an A, or barely passing, depending on your perspective, would be like a C or a D minus. Okay, with that, we need to recognize that this relates only to the bond. So in the next segment, we're going to talk about compounds or molecules.